All right, in this video, we're going to be discussing binary numbering systems. Now, we've talked about numbering systems in general in a previous video. So we covered in that the decimal numbering system, which most of us are familiar with and use on a daily basis. We covered a little bit of the binary numbering system, and we covered hexadecimal, just a little bit of that as well. Here we're going to do a little bit more of a deep dive into the binary numbering system. So we're going to start by talking about this concept of bases again, which we referred to in the previous video. The binary numbering system is a base 2 system. It's a base 2. Which means that we have two symbols that we use to represent all quantities within that numbering system. We use 0 and 1. Now, this is convenient. We use the binary numbering system quite a bit in computer networking, as well as within a computer itself, within the actual box. It's how a computer operates and communicates internally. And it does that because this 0 and 1 equate really to the notion of on or off, or true or false. Okay? So it's very easy. Internally in a computer, it's just like flipping a switch. 0 is off, 1 is on. And the same is true in the concept of networking. We develop and construct IP addresses using the binary numbering system. We often break this up into 8-bit segments. And you may have heard of a 32-bit system or a 64-bit system. Those systems, obviously 8 is a factor of 64, a factor of 32, so it's easy to manipulate those values. And so that's why we use it. So what we're going to do is we're going to start with an example. In this first example, we're going to turn all the bits on. We're going to give ourselves space for 8 bits, 3, 4, 5, 6, 7, 8. And in this particular scenario, we're going to turn them all on. And the reason we're going to do that is so that we can illustrate what this 8-bit adds up to in terms of a decimal value and show what it looks like. So we'll put a 1 in each one of these. If any one of these had a 0, well, it would be off, and we wouldn't use it to calculate any value, whether it be decimal or hexadecimal. This is going to be 2 to the 0, and if you watch the previous video, you'll see why these exponent values work and how they work. 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6th, and 2 to the 7th. Now, if we calculate each one of these exponentially, this is going to be 128. In terms of a decimal value, this is going to be 64, 32, 16, 8, 4, 2, and 1. Notice that as we move up, starting at this initial value, we're simply doubling the number each time. This is another convenient aspect of using the binary numbering system, is this doubling each time. It makes some of our calculation processes pretty easy, especially when we're dealing with larger numbers and when we're dealing with IP addresses. So if we were to total all these up, they would add up to 255, the value 255. So now what we're going to do is we're going to just pick a random decimal value and illustrate how we can change that value to a binary value. So we'll just pick a value, 233. Okay? And for the sake of this illustration, let's draw out these places again. So 1, 2, 3, 4, 5, 6, 7, 8. And we're going to add a ninth place. And here's the reason for that. So we have 2 to the 8th, 2 to the 7th, 2 to the 6th, 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 squared, 2 to the 1, 2 to the 0. And if we work our way back up, this is 1, 2, 4, 8, 16, 32, 64, 128. And we know that this value is simply going to double from 128, so it's going to be 256. Okay, so the reason we added that value is to illustrate the fact that we have this value of 233 in decimal. We want to convert it to binary. So if we look at the decimal value of this ninth bit, we realize that it's 256, which is more than 233. So we're going to turn that off because it's too big. It doesn't work for us. And we're going to look at the next bit, and it's 128. It's beneath the 233, so we can use that value. So what we're going to do is we're going to begin to subtract 233 minus 128. And that's going to give us a value of 105. 105. So we're going to turn that bit on. And we notice that our value of 105 is larger than our next bit, which is 64. So we can use that bit. We'll turn that on, 64, and we're going to subtract that. And that's going to give us a value of 41. Okay? 41. Well, we look at that. We look at our next bit. Our next bit is beneath this value. It's lower. So we can turn that bit on because we're going to use that. And that's going to give us a value of 9. Well, our next bit equals 16. It's too large. It's larger than 9. So we're going to turn that off. We're going to bring our value of 9 up here and subtract 8. That's going to give us a value of 1. Well, the only one that's left that equals 1 is our last bit. So we're going to turn that on, and we're going to turn those two off. And what we've just done is we've converted that decimal value of 233 to the binary value. So we could say this, that 233 equals, I believe it's, I have to look back here, yeah. So it's 11101001. So 233 in decimal equals the binary value that's listed here. So that's a conversion to that. Now, what we want to do is we want to take this a step further. We're going to convert that binary value to hexadecimal. And in order to do that, I want to just review the base system for hexadecimal. We're going to use all of our decimal values, so we could use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But that only gives us 10 values, 10 symbols to work with, and we need 16. So we're going to be using letters. And if you remember from the previous video, I illustrated this in that video, so take a look back at the numbering systems video. And essentially these will equal 10, 11, 12, 13, 14, and 15 in decimal value. Now we're going to bring this binary value down. We're going to break it up into 4-bit segments because it's easier to work with. And the reason that we do that is that 2 to the 4th is equal to 16, which is our base. So it's very easy to work with these 4-bit segments in transferring those over to a hexadecimal value. Well, what we realize is that in binary, this value is 2 to the 3rd, 2 to the second, and 2 to the first. 2 to the third, 2 to the second, 2 to the first. This one's turned off, so we're not going to use that. This is 2 to the third. This one's turned off. This one's turned off. This is 2 to the 0. Okay, so 2 to the third, this is 8 in decimal. This is 4. This is 2. We're not using that bit. This is going to be 8, and this is going to be 1, and we're not using either of these. So this is going to be 14 times 16 to the 1, and this is going to be 9 times 16 to the 0. All right, well, we notice that our 14 in hexadecimal is E times 16 to the 1, and 9 times 1, so that's just going to equal 9. And so our hexadecimal value is just E9. That's our hexadecimal value. So we've just converted that from binary into hexadecimal. Now, if we were to take this even a step further and come back to this and realize that 14 times 16 equals 224, and we add 9 to that, we're back at 233. So what does this all tell us? Well, it tells us that 233 equals 11101001 in binary, and it also equals E9 in hexadecimal. Hopefully, again, this is another snapshot of how we move from one numbering system to another. We're highlighting here the binary numbering system, so we converted from decimal to binary and from binary to hex.